signals. And we have a pretty exciting antenna refurb program on the E9. E9 is an aircraft that's owned by the U.S. Air Force and resides at Tyndall Air Force Base. And what I'd like to tell you a lot more than I'm actually going to be able to tell you. And I was told to keep my hands in my pockets because, you know, when I start moving my hands, I start talking. So I'm going to go pretty quickly, and there'll be options for questions. I'm going to try and leave some time for questions at the end. So I'm going to start with the legacy hardware. And I'm going to describe what it is we did in the upgrade, how we came about the solution. I'm going to show you some pictures of the actual hardware, some measurements and performance data that we have. We'll talk a little bit about the development team, which is spread across the country, and then give you a current status and summarize. Of course, if there's a chance, I'm going to talk to you about the design notes, which I don't think there will be a chance to talk about. There's lots of pages here, and of course I'm going to talk very quickly. So this is a picture of the actual aircraft. This is the Havilland aircraft. It resides at Tyndall Air Force Base, and it supports telemetry operations over the Gulf of Mexico, which is the Evelyn Gulf Range.
Push button again. Yeah, you right and left buttons.
Okay. Sorry. It's a weapons evaluation program, and the antenna itself has 10.5 dB GOVT at foresight. It has 5 beams that are dual linear polarized, patch radiators, an LNAH element, and a phase shifter for every single beam, which makes it 10 per element. It's azimuth steered only, fixed in elevation. It has 4 additional racks of equipment, and that's an RF receiver for each polarization. There's a 2 input diversity combiner for each beam. There's a lot of equipment, and that's what we're trying to replace. This is a U.S. Air Force asset. It's operated by a company called King Aerospace in Panama City. It's at the Havilland -8, and the antenna was built more than 20 years ago. It's a conventional phase array using diode phase shifters, and its controller is a DOS-based 286 processor, which runs at 8 megahertz. And as you can imagine, at this point, it's getting to be difficult to maintain. In addition, the missions have grown. There are a lot of new requirements, including more simultaneous targets, new modulation schemes, and longer flying times. So what we're trying to do is double the number of beams to address the number of targets. We're going from 5 to 10. It's actually 20 beams because there's 10 at each polarization. There's the extended elevation coverage. It has been a fixed 10-degree elevation beam, and right now we're trying to cover the space between plus or minus 15 degrees for a total of 30. Same physical envelope to prevent going through the FAA certification process, and that's 33 feet long and about 2.5 feet tall. Trying to stay within the same power budget, hopefully get less weight, and with new modulation schemes, such as some of the new ARTM modulations. This is really an eye chart, but what I'm trying to go through here is the process by which we came up with synthetic beamforming antenna. In the 70s and 80s, phase shifters were expected to drop in price significantly just because of the large demand placed on them from the radar industry. However, that didn't happen. So now digital speeds are getting to the point where RF hardware is no longer an exclusive trade space for telemetry frequencies at S-band. It's always been true that once you're in the digital domain, the system capability is pretty much determined by how much signal processing horsepower you have. And 2 things are happening. The cost of signal processing is going down, and the speed is going up, as is the gate density. And in addition, in a parallel path, which is slightly related, manufacturing techniques are allowing miniaturized hybrid products to be made at reasonable cost. So when you put all this together, you have certain things that we have no choice about, like the RF elements. You can't, digitize the element itself, so that stays at S-band. Some of the things like LNBs are able to be made using production assets that have been streamlined, and so we want to keep those in hardware. But some of the more expensive components, like signal distribution, phase shifters, filters, receivers, and diversity combiners and demodulators, all are moving into the digital domain. The moment you move the phase shifter into the digital domain, you become a synthetic beamforming antenna. So here, what I'm trying to show is the coverage volume that's required for this application. And it's 100 nautical miles out, and it has 50,000 feet altitude. And it looks like a squashed, it's like a pill. And there's allowed to be 6 dB of degradation as you move out to the edges. So the radius here is 50 miles, and over here it's 120 degree scan volume. So what you see here in the red is the G over T requirement to make successful tracks over the entire volume, and that's kind of a cosecant squared type of a shape. The blue line is the existing antenna beam, or what you can have. And what happens when you use independent apertures, you split that aperture into different pieces and you combine them with different phases, is that you're able to spread this energy out a little bit and cover the cosecant squared pretty well. Right now, if there's a target in this region, the E9 flies at a kilter, and it's become quite a challenge, and some of the operators have been known to lose their balance. Right, guys? Here's a cartoon of the antenna. The antenna itself, this is that same picture that you see here, and we're towards the back with these radiators. This is a mechanical arrangement, and they're called subarrays, the mechanical parts, but they do not and they're made to coincide with the structure of the aircraft, or the bolt-on frame on the aircraft. The electrical parts do not coincide with the mechanical parts because the electrical parts are there for GOT reasons. And what you see is unequal sized apertures in elevation and equal sized apertures in azimuth. And on the edges, there's some parasitic elements to try and keep the impedance of the edge elements to be the same as the ones in the middle. If you take the smaller of the apertures, and we're talking about an elevation pattern now, take the smaller of the apertures, you see this broad beam, which is in the magenta. You take the larger of the apertures, you see the slightly narrower beam, which is in the black. If you put them together and combine them with a fixed phase, you see the blue one, which is the current antenna. And if you choose to combine them with variable phases, you see the green one, which gives you a lot more effective coverage. So in azimuth, we're using 2 apertures. Sorry. For monopulse tracking. In elevation, there are 2 unequal apertures to give us this funny shape, and they're combined using their relative phase, the insertion phase, the relative insertion phases, and a signal quality measure, which is designed to consider signal contamination due to multipath. Now, the E9 flies over water most of the time, so multipath is our friend. And